if I asked you to identify three types of numbers, you may say something like 1, 2, 3. That would be three types of numbers. In fact, these are not different types. These are the same type of number. They happen to be different values, but they're not different types. So let's look at four of the different types of numbers that we will work with in algebra. Later, you will learn more, but we want to start with some more familiar types that you've seen before, but not necessarily thought of as individual number types. So we have integers, and rational numbers, and radical numbers, and polynomial or monomial numbers. Most of algebra is exploring polynomials, but we're going to start the year by just talking about the simplest form of a polynomial, which is called a monomial. All right, well, what makes each of these numbers whatever they are? Well, the integers you've worked with a lot. You may even know that name, and you may even know what they are, so I'm just going to clarify it a little bit. Integers are the numbers that you would have started with maybe up here when you naturally thought three different types of numbers. There's 1, 2, and 3. Those are actually called natural numbers or counting numbers. They're the ones that we automatically naturally use and the ones that we use to count with. So the natural numbers are part of the integers. Another part of the integers are all the numbers on the other side of 0. So if you were to draw out a number line, you'd have 1, 2, 3, dot, 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 all the way to infinity. And then on the opposite side of 0, you would have the opposites, -1, -2, -3, dot, 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 all the way to negative infinity. So natural numbers, they're opposites. And 0, the number that you're flipping over to get the opposites. So basically, the integers are the numbers that when you sketch up a number line, you automatically put the integers on. You mark 0, then you make a bunch of tick marks and you label them 1, 2, 3, 4, 5 on one direction, and -1, -2, -3, and on the other direction. Those are the integers. Easy enough. Rational numbers. Now you might think rational numbers, ratio, must be a fraction. They are fractions indeed. Rational numbers are fractions, but they're a very specific kind of fraction. You must have an integer in the numerator, and you must have an integer in the denominator. All right, so you can't have something like pi over 2, right? So pi divided by 2. That is not a rational number because pi is not an integer. So an integer over an integer. A radical number is any number that contains this symbol. That's a radical symbol. Right now, you probably think of a radical symbol as always being the square root, but there are other forms of radicals than square roots, and you'll learn those later. But right now, the most important thing is to know that the name of this symbol is a radical symbol, and any number that contains that symbol is a radical number. And then a monomial or a polynomial, these are numbers that have a variable in them. All right, so they get a little bit more complicated than just that later on. We're not going to worry about that too much. We just want to work with identifying what kind of a number we have if we're given a number, and we want to convert all of the numbers that we work with from one type to another. For most of these, practice will make perfect, but I'll give you shortcuts that you can memorize how to work with, and with practice you'll understand more and more what's happening. So let's start with a number like 5. 5 is a nice simple number. First, let's decide what type of a number it is. Well, obviously it's a counting number, so it must be an integer, and indeed it is an integer. But let's convert 5. We want to know if it's possible to convert 5 to all the other types of numbers. And in fact, 5 can be a rational number, because if 5 is an integer, I can always write 5 as the fraction 5 over 1, which means 5 is an integer, 1 is an integer, so 5 has now been converted to a rational number. But I'm not limited to 5 over 1. Any expression that is equal to 5, that is an integer over an integer, is a rational number. So I could have done 25 over 5, or I could have done 100 over 20. All of these numbers equal 5 if I reduce them, and all of them are an integer over an integer. So they're all conversions of 5 into a rational number. Can I turn 5 into a radical? This is the one that's not going to be so instinctive or instinctual, but I know that the square root of 25 has the value 5, right? The square root of 25 equals 5. So now I've converted the number 5 into a radical number. And a monomial, well, the trick here is to write a number that includes a variable, except you have to identify when it's true. So 5x equals 5 only when, and that's what the semicolon means, when x equals 1. So I've now converted the number 5 into a monomial because I've added a variable, and since I've identified the right value for that variable to equal 5, or for the whole number to equal 5, I've made the conversion that I wanted. So let's look at -3 this time. Well, -3 is the opposite of a counting number, which means it is an integer. And I've already shown that I can turn any integer into a rational number by writing it over 1, or writing it in some form of -27 over 9, because -27 divided by 9 equals -3. So I know I can convert an integer to a rational. Now the radical, I have to look at a trick here, or I have to show you a trick here, because you're not going to necessarily know instinctively all the radical values that convert easily, because you haven't worked as much with radical numbers as you will by the end of this year. So I'm going to show you a step to use, or a trick to use, and you just need to practice it. I'm going to use the first one. It was easy for you to see that the square root of 25 equals 5 because 25 is a perfect square, and we sort of have it in our brains all the time. But ask yourself, what did I do to get there? Well, actually, don't even ask yourself that. I'm just going to show you the trick. To find out what value has to go inside, what I want to do is multiply the initial value twice. So 5 times 5 equals 25, and that's the number that is inside the radical. And that's how you convert a number to a radical. If it's possible to convert, that's a step to do it. So in this case, I'm going to say -3 times -3. Well, that equals 9. So I've converted the number -3 to a radical number by multiplying them together. And be careful here, because I know that you're used to seeing, whenever you deal with a radical, you can't possibly be dealing with a negative number, that this -3 and a radical sign don't go together. But notice I didn't write the negative inside of the square root symbol. I wrote the negative outside. I squared the number, and it turns out that the square root of 9 is -3. Now, the square root of 9 is also 3, but you'll talk about that later, that there are two answers for that problem, or there are two ways to reduce the square root of 9 to an integer value. But follow these steps, trust it, I wouldn't lie to you, and you will convert a negative integer into a radical number by using this step. And then on the monomial, to convert -3 to a monomial, same thing. -3x, and you just say, well, x has to be 1. So if x is 1, -3 times 1 equals -3. In this case, you had another choice, though. You could have said 3 times x and just identified that x has to equal -1, because -1 times 3 equals -3. So in this case, there were two ways for you to convert the negative integer into a monomial. So let's look at a number like, 3/5. All right, well, 3/5 is definitely not an integer. Integers, we've already talked about, are all the numbers that you put on the number line where you line up 1, 2, 3, 4, 5, 1, 2, -1, -2, -3, -4, on in that direction. 3/5 falls right between those two. It's somewhere in between 0 and 1. And since it can never fall, 3/5 will never be on one of those counting points or the opposite of the counting points or at 0, then this is not possible. So we can't convert a rational number into an integer. Interesting though, right? Because I can always convert an integer into a rational, but we can't necessarily convert in the opposite direction. All right, so I can easily write 3/5 as a rational number because 3/5 is a rational number. Now, radical. Well, I have a rule, right? 3/5 times 3/5. Well, that's multiply across equals, well, let's just go this way so I don't have to write it twice. Multiply across equals 9. Multiply across the denominator is 25. And so the square root of 9/25 is the same thing as 3/5 converted to a radical. And then to write a monomial, we'll just use our easy trick, 3/5 x, making sure that x equals 1. Now, you could write a whole bunch of values you could change what 3/5 is and then make x something different so you get there, but that's not really, we're not looking to make it as hard as possible. We're looking to convey the idea that numbers that belong to one group can be changed to look like numbers that belong to another group. As long as the value is the same, you're okay doing that. So let's look at a radical, and I'm going to look kind of at a tough radical. I'm going to show you an easy one first, and then I'll show you a tougher one. So if I were to say the square root of 9, well, the square root of 9 equals 3, so it's definitely an integer. Well, the square root of 9, if the square root of 9 has a value of 3, then I could certainly write 3 over 1, right? So I've converted the square root of 9 into a rational number. That's easy enough. Converting it into a radical doesn't need to happen. It already is a radical. And converting it into a monomial, no problem. I'll just use my easy trick, the square root of 9x, where x equals 1. But I want to actually show an example that isn't so easy to deal with. What about the square root of 3? Right? So the square root of 3, could that ever be an integer? Well, if I look at the number line, square root of 3 is not a perfect square. The square root of 1 is the same as 1, and the square root of 4 is the same as 2. So the square root of 3 has to fall somewhere in between 1 and 2. And we already know from the previous example that it's not possible for a number that just lives in between two integers to ever become an integer. So let's look at turning the square root of 3 into a rational number. Well, a rational has to be an integer over an integer. Since the numerator is not an integer, right? Not an integer, and this is the symbol for integer, a little fatty z. Not an integer, then even if I put it over 1, it's not possible to turn a irrational or not rational number into a rational number. Radical, still not a problem. That's square root of 3 is the square root of 3. It's a perfectly good radical number. And it turns out that it's okay for you to have a radical that can't be turned into an integer in a polynomial, as long as you say that x equals 1, so that square root of 3 times 1, anything times 1 equals whatever itself is. So sometimes you can't turn numbers to all the other number sets. And then last but not least, let's turn a polynomial. Well, we've already said it's a polynomial, so let's just go ahead and write it here. It's a monomial. So we're going to write it here under monomial. Can I turn this monomial into an integer? The only requirement for this monomial to be an integer is to have it be an integer, right? And since I have an unknown part of the number, so I have 2x, I can choose anything that will make sure that 2 times that number equals an integer. So choose x equals 3. 2 times 3 equals 6. 6 is an integer, done. I could have chosen x equals 9. 2 times 9 is 18. 18 is an integer. I'm good to go. Same thing here for a rational. I can choose 2x over 1. And I know that the numerator is an integer as long as I identify a value for x that makes the numerator an integer. And I'm going to use the same value here. So now I have, if x is 3, then 2 times 3 is 6. 6 over 1 is a rational number. It's an integer over an integer. Turning 2x into a radical. Nothing says you can't have a variable inside of a radical symbol. I'm going to use the trick. 2x times 2x. You should have done simple monomial multiplication in pre-algebra, so 4x squared. So 2x times 2x is 4x squared, and then we already had it as a monomial.